So as far as parameters are concerned, if you have a sequence length of 4, the parameters for each hidden neuron are just going to increase by 1, this is per neuron. As far as the other parameters are concerned, they are going to pretty much remain the same. So limitation of RNN is that when we train our networks with long term dependencies, the backpropagation through time, when we train our networks through long term dependencies, the backpropagation through time leads to something called the vanishing gradient. So the idea is that if there are several gradient values v1, v2 and so on, and the absolute values of these v's turn out to be less, the multiplication of v1 with v2 and then v2 with v3 and so on, which happens courtesy the self loop on each perceptron, this leads to the gradients becoming very small and actually tending to 0. The product of these gradients is basically going to lead to no updates for some of these states. One might say that you could use an alternative function that gives value greater than 1 as output, but this will have the other problem, which is your gradients might simply explode. So the idea is to be very selective about which states to use to predict the next state. Do you really need the entire history to matter when it comes to predicting the state based on the current input? So the vanishing gradient problem has been shown here with respect to the unfolded network. So inputs have been shown here on below, and there are indices up to 7, and there are hidden layers and outputs which have all been summarized across all the neurons in the hidden layer. The sensitivity of the network with respect to the input, that is the input at t equals 1, varies or decays as you move away from the input, and in fact this decay is exponential, has been pointed out here. So for time 7 steps, you find that the first state is extremely sensitive with respect to the input, or rather the configuration at time equals 1 is sensitive to input at time 1, but then the effect of gradient update across these time steps is drastically reducing, exponentially reducing, so much so that any update you do at the 7th state and try to reflect that on the weights that should have been at the hidden layer configuration corresponding to the first time step or the first index is going to be practically 0. So the effect is really vanishing. The solution to this is long short term memory. The idea is we want long term memory but very selectively. So the solution is memory that captures selected history. Selection aspect is what short term is about, and the history component here is what long is about. So procedurally this will mean you learn when to propagate gradients and when not, depending on the sequences. You use the memory cells to store information and reveal it whenever needed. So you are going to basically have something called a memory cell which stores information on when to propagate and when not to propagate. So for example, if you have I live in India, I am certainly interested in the fact that I have seen in India when I try and look at the next possible location. So if I have to predict the location to be a city, I would rather look at cities in India. So you are trying to remember the context India as it's generally related to many other things like language, region, etc. However, once we have mentioned Mumbai, you might want to forget India because you are interested in attributes of Mumbai and not generic attributes of India. More about the long short term memory in the following discussion. Thank you.